In this section, we'll look at the two-stage amplifier, the compensation. This is the typical two-stage amp model. So for each amplifier, for example, we can model that what GM and the output impedance are out, right? But the problem is, but thing is that once we include that R out, our analysis a little get messier and complicated. So we can assume that R out is infinity. The DC gain is infinity, right? GM times R out is infinity. Based on that, then each amplifier stage can be modeled as a GM stage, right? Like this. Now, since at DC, we assume that that is ideal gain, so we can find some approximation or approximation at midband. So we are gonna drive the equation at midband, right? So midband equation. So basically, we don't care about the DC gain, okay? So in that case, so typical amplifier, two-stage amplifier GM1 and GM2 will be cascaded like this. Now, what we have is that by inserting compensation capacitor, so without this CC, what we would have, without CC, the problem is we have high output impedance, which are both closely spaced each other, so that will create two poles, more than one pole, so two poles below the unity gain frequency. So to make one pole dominant compared to the other pole, we add CC there, and this will generate the large capacitance by the effect of the Miller effect. So Miller effect, we can assume we know that small voltage variation at the other terminal will be amplified version of the voltage will appear on the other side. So the effective C capacitance will be boosted by the voltage gain. That's something that we had learned by the Miller effect, right? So using the Miller effect, we add the capacitance. So this is called Miller capacitance. The effective gain. So at node 1, thing will be very large capacitance there. So now our analysis is that the dominant pole will be at the node 1, somewhere in the node 1, the pole by the node 1, and the second pole will be at the output side, right? So omega p, like this is fp2, so f2, and this is f1. So this is something that we want to have in our scenario, and so f2 is f non-dominant pole, and f1 is dominant pole, right? Now let's find out the unity gain frequency. How we can find that? So think about at unity at the midband here, the signal at the capacitance left hand side, node 1, signal will be very small, and signal will be very large on the right hand side. So the first stage will be GM stage. So input current, so GM times VI, the input difference VI, right? So now the positive on the bottom side, so plus minus the VI. So VI, so we have the current, input current flows, and the only way this current can flow is where that is only through the CC. This current will flow through the CC like and generate it. Now, since the second stage gain is very large, we can approximate this node 1 is AC ground, because the second stage gain is very large. That means the voltage across the CC, voltage drop across the CC will be, right? So V out will be what? The voltage drop minus voltage drop over CC, right? That would be minus what? The GM times VI times 1 over SCC, right? So based on that, we can drive that at midband V out over V in VI is that what? Minus GM over what? SCC, meaning omega U over S. So based on this derived equation at midband, neglecting the DC gain, right? Omega U, so FU here is what? 2 pi GM over CC, right? We can easily get that, right? FU. Now, once the FU is found, we need to find out the non-dominant pole location, the F2 location. How we can find that? Because the CC is very large at the midband, we can approximate the second stage, what? GM, here GM, and the short connection, and the RL, and the CC, CL, there, right? If the RL is much larger than GM2, so RL is much larger than 1 over GM2, then we can approximate the second pole location is that 1 over GM2 over CL, right? That would be the omega second pole location. So in frequency we can get the GM2 over 2 pi times CL, right? So this is at midband. So basically CC impedance becomes close to 0, very low impedance. So it looks like we can treat that as the short connection. So now we found out the GBW frequency and non-dominant pole frequency, right? So based on that, we can see that, we can find that what? The relationship between FU versus Fn. So Fn, non-dominant pole, must be greater than FU to make this amplifier, if that amplifier used in the negative feedback, we want that to be non-dominant pole is greater than FU, right? So basically, this amplifier gain plot will be the what? Same as what? Loop gain, right? With beta equal to 1, right? So the loop gain plot, we want that non-dominant pole is greater than FU, right? So as you can see here, what you can see is that so for similar size of the CC and CL, you know that GM1 and must be smaller than GM2. So the second stage GM2 typically must be larger than in GM1. Okay. So we will see that requirement more in detail in the next slides. Okay. So in a typical amplifier, it will have a finite input capacitance, that is Cn1. If you consider that, the non-dominant pole calculation becomes a little different. So the the output equivalent impedance that there would be, you have to find the voltage division. So you have previously with the only capacitor, we treat that as short connection because this is the input is infinity impedance, so no current flow through the capacitor, meaning the zero voltage drop. It looks like a short connection, right? But if you have a finite Cn1, then you will get the voltage drop, voltage division. So equivalent test voltage here, the voltage here will be T times Cc plus Cn1 times what? Cc, right? So this kind of voltage division relationship that will result in effective R out will be, if you calculate the R out, would be previously was without Cn1, it was 1 over Gm, but the effective Gm become reduced by that factor, the Cc plus Cn1, right? Like this. So Gm ding ding ding. So what? 1 plus Cn1 over Cc, like this, right? Something like that. So what? So non-dominant pole location would be modified by that factor there, right? Let's design the small signal parameter. So if you remember, so if the non-dominant pole location is 3 times GBW, then that results in what? The PM, approximately PM close to 70 degree, right? So previous example. So FU and second pole F2 must be 3 times FU. Then the result in PM equal to 70 degree. To target that, how we design that? So assuming that parasitic capacitance versus CC ratio is, or let's say around the 0.3 there, then using that factor, we can get the approximately GM2 versus the GM1 is 4 times CL over CC, right? You can get this the result, right? So for example, for GBW 100 megahertz, for CL equal to 2 picofarad, and you can find that and plug that in that plug that into there, so we can get there. How much then? If we choose that GM2 GM1 relationship, then what? 2 picofarad. So CC, let's choose what? How much CC we will choose? So because the load capacitance is 2 picofarad, to drive the 2 picofarad, the compensation capacitance, and suppose you would like to have less than CL load capacitance to save the area. So let's make it half of that, right? Half of the CL, that give us some kind of a good margin. I mean, good area efficiency. So that results in what? 4 times 2, meaning 8. So GM2 must be greater than GM1 by 8 times, right? Approximately 8 times greater GM is implemented, then that results in what? F non-dominant pole with location would be 3 times FU, right? That leads us what? The PM equal to 70 degree, right? This is very important result. So you have to design that second stage GM greater than 8 times, almost 8 times greater than first stage GM. That give us our desired value, right? Desired the target phase margin. In this slide, we will see more detail regarding to the transfer function derivation. So in the previous example, we had assumed that just midband approximation so that the DC gain is infinity. But right now, we will just plug in the output finite impedance, finite output resistance of the first stage. That means the first stage gain is GM1 times Rn1, and the second stage gain is GM2 times what? RL. RL is the output impedance of the second stage. Considering the Cn1, so we can derive the equation, and the voltage gain we will find like this. So on the bottom we have 2 poles here. 2 poles, and on the top numerator, so we have 1 0, the 1 0, but this is positive 0, 1 positive 0. Positive 0 is very bad because it adds it deliver additional phase shift. Right? Phase shift that will reduce the PM, right? PM goes down. So this additional phase shift should go away much higher frequency, or it should be way above the unity gain frequency. Right. So one thing that you can take a look at is on the denominator, we have a very complicated equation. There's a second order equation, but as you can imagine, so our transfer function will be like this. So the dominant pole here, the second pole way above the omega gain, second pole is way above the omega u, right? So this dominant pole and second poles are very widely separated. So we can do some approximation for these cases, right? So for this, so to recapture, the omega u was what? So GM1 over CC, right? And the F2 is the location of the omega 2 is what? Close to GM2 over the what? CL, approximately. If the Cn1 is the 0, then it will close to GM1 over CL, GM2 over CL. So the GM must be a lot larger. So, and also we have the 0. The 0 is where? 0 location SG. So omega z is what? GM2 over CC. So GM2 over CC should be, so typically CC is smaller than the what? CL, so it will be like that, right? Something like that. So going down, going up, so the 0 here, omega g, considering that. So if you consider the CN1, then the omega 2 might the effective GM2 will go down, right? So it will go below, like it will go down, right? Something like this. And so omega 2 location can vary, right? It may be a little higher or lower. So actual, let's say, actual omega 2 will be slightly less than this GM2 over CL, because the effective GM2 is smaller by this CN1, right? Okay. So let me draw some different let's say different color like this. So overall response about something like this, right? Yeah. In the previous derived equation, it was very complicated in the denominator. So we can, let's say, if we assume that dominant pole and non-dominant poles are widely separated, let's say 1 plus s omega p1 times 1 plus s omega p2 will be like this, right? On the bottom, let's say 1 minus cs, right? A0. So this one, so 1 plus 1 over omega p1 plus 1 over omega p2 plus s square omega p1 omega p2. So if the omega p1 and omega p2, so one of the omega p1 is so small, then the coefficient of the second order terms will be very small, and this the first order coefficient, it will be approximately 1 over the omega p1, right? Because the dominant pole is a lot small value than omega p2, right? So we can do some approximation. So the dominant pole location will be 1 over a, the coefficient of the first order, the first order coefficient is a, then the pole location would be 1 over a, right? According to like this. And then second pole location would be a over b, the ratio between the first order coefficient and second order coefficient b, that will give us the second pole location according to here, right? The what a is the, let's say, 1 over omega p1 divided by, let's say, omega p1 omega p2, like this will be what, omega p2. So this is something that you can use. This is called the dominant pole approximation method. When you have a complicated second order equation terms, you can easily find out and poles and zero, even without solving this second order equation. Okay, you can get the approximate value. To summarize the two-stage amplifier design procedures like this, for the given CL load capacitance, we choose the compensation capacitance, but the size of the compensation capacitance must be smaller than load capacitance. In that way, we can use the area more efficiently, right? And the another reason is that you will see that the so another region for CC should not be that the larger than the CL is that, let's say we had the pole and zero location. The pole location is, let's say, non-diagonal pole omega P2, and then zero location omega G. So omega P2 is approximately what? The GM2 over CL, and omega G is GM2 over CC, right? If the CC is larger than CL, then what happened? So zero appear first, right? So that means the transfer function zero appear first and then pole, right? Something like that. Meaning, if CC is greater than CL, then what? So omega G is below. So omega G is below omega G below omega P2, omega 2, right? P2, meaning less gain margin. The gain margin become bad, right? So we want that to be going down, straight down, following the 20 dB per decade, but it will boost up the gain near FEU, so that will be reduce the gain margin. So this is the second region, right? For first region is area, better area. And second is this region, right? So omega G greater than omega P2, right? So if still, so this is the first step. So choose CC less than CL or similar or less than equal. That would be something that the guideline, right? And then if the still not enough PM, if you don't have enough PM, then what you can do is that just increase the GM2 so that the pole and zero location going further away from the omega U, right? So how? So there are several ways to increase the GM. You can have a larger, you can size up or scale up this the output stage. That will result in more current, right? For example, if the CC is half of the load capacitance, and then the relationship from that, we can get the GM2 must be 8 times larger than the GM1, right? So if we just simply assume that for the same overdrive voltage, 8 times larger GM require 8 times larger current, right? Because the GM is proportional to 2I over overdrive, right? But typically, the first stage GM designed much smaller overdrive, so that the GM efficiency is better. I mean, we increase the so GM efficiency. So it is defined by what? The GM over ID, GM over I. So increase this efficiency so that for the same amount of current, you get the best possible GM, right? So you have to design that in the first stage to have a small overdrive voltage for the first stage. Then we can get better current efficiency. So we can we can avoid too much current on the second stage, right? By having this, right? Having smaller overdrive in the first stage, right? Typically, GM efficiency drive that more than 10, right? And the last point is for larger CL. If you have a larger load capacitance, if you want to drive the larger CL, then what we have to maintain that. So like this relationship, this relationship still. So if the CL larger, what you have to do is GM2, either GM2 both increased or CC also increased. So we have to increase both GM2 and CC, right? So this is something that you have to consider when you design the two-stage amplifier. Okay. In the two-stage amplifier with the Miller decompensation, we had seen that in the denominator, in the numerator, you had the zero, right? That is positive zero. Let's take a look at the effect of the positive zero in more detail, and also we have to compensate that positive zero because it results in additional phase shift, right? Phase shift, additional phase shift of 90 degree is caused by that positive zero. So we have to avoid that. So we have to remove that effect of the positive zero. That is called the compensation of positive zero. Okay. This is the example of one negative zero and positive zero. The equation shows that one pole and one zero. For the negative zero, let's say we have a pole at F1 and pole zero at F2. For the negative zero, the phase shift is positive. If you look at this angle, that angle is positive. So the phase shift around the first pole will be in the 45 here, right? And then the phase will start decreasing. Phase shift happen approximately 1/10 of the F1, and it will stop at approximately the 10 times F1, right? So it will be something like this, and then F2 will have the positive phase shift. So the negative phase shift is kind of compensated, finally going back up to zero phase shift, right? But on the other hand, the positive zero results in the additional phase shift, right? This is the negative phase. So if you calculate the angle, that is negative. So the first pole, right? This is 1/10 of the F1 and then 10 times F1. So in the middle, at F1, we have the minus 45 degree phase shift. And then near F2, we start decreasing again the phase, right? So overall, even though there is one pole there, the phase shift is already 180 degree after this second zero, right? This is zero, right? This is zero. At the F2, we have a zero. So this is something that we have to avoid. We have to remove this kind of zero, okay? The generation of the positive zero in the Miller compensation is kind of problematic. So we would like to see how this positive zero is happening. So positive zero is can happen. Let's say, for example, the zero, as you can see, the plus minus AS, something like this, CS, let's say, the same notation that we had used before. So for this case, you can imagine that there's some path, which has a frequency, the phase shift causing phase shift, any block causing the phase shift. It might be the additive or the subtractive. Then you get some kind of this kind of positive zero or negative zero happens. So in the circuit, if there's any path that having two paths merged at the output, but the other path has some frequency dependent components, then you would introduce the zero. In the Miller compensation example, we have the CC compensation in the feedback. So the signal path is one is through the capacitance, the other is through the amplifier itself, right? So this amplifier, in that case, is it additive? At the output, our signal current will be added. So is that the subtractive or additive? So if you imagine there's any current going into this node, the voltage will go up, right? So that will, let's say, Vx. The Vx will draw the current back to, right? So Gm. So final load current to the output is subtracted Gm Vx. So this current, let's say, this current minus the output, minus the pull down current. So the output voltage, you can say that the current going through the CC is that if the output is so in the zero, if the output is zero, approach to zero, so you force that to zero, then the Vx over 1 over SCC current is exactly balanced, right? So subtractive, that is equal to Gm, let me say, minus, let's say, Gm Vx equal to 0. I'm sorry. So this is not sorry. So we have to draw that okay. So what, Vx over 1 over SCC. So that give us what, Vx SCC minus Gm equal to 0 for all Vx. So the S equal to Gm over Cc, right? So we have a positive 0 happening. So this kind of positive 0, you can think of the at the high frequency, the amplifier second stage GM is not working, for example, then you will see that this kind of a signal coming in, then it will feed through the same phase output. But if the amplifier GM2 is the working, then it has the inverting output. Each output is an inverted version of the input, so we have an amplified version of the voltage at the output, but each phase is inverted. But the feed forward path, it just feeds forward. It's the same phase happening. So this, so you can imagine that this is whether you can say that through amplifier operation, each phase is inverted, but the feed forward path, its phase is what, the same phase. So those opposite phase addition results in the what, the subtractive addition, right? So that gives us what, the positive 0. You can understand that intuitively like that. So if you add some signal in destructive way, then we introduce the 0. So add the signal in a destructive way, positive 0. On the other hand, if you add the signal in phase, I mean, if both signals are in phase, then the resulting 0 will be negative 0. So left half plane 0. Okay. So positive 0 results in what? Additional phase shift. So that causes the PM goes down, right? it looks like an additional pole in there at that frequency, right? In phase response. The additional phase shifted down, right? So to remove that, the zero, so we had one path and the other path which has some frequency dependent components added together. So subtractive way minus plus and minus, something like that. So to remove that frequency dependent component is added at the output, right? The signal is different from the other signal path in phase, right? Different phase addition. So to avoid that, what we can do is that we disconnect the feed forward path, but we still maintain the Miller effect. So to do that, we add one way is the add amplifier here, so that the feed forward path is the forward path is avoided. So because the amplifier impedance is low, so signal can pass through the amplifier the other way. So as the amplifier only pass input signal from the input to output, right? So one example is like this: source follower. So the amplify the signal just pass through this amplifier, right? Just level shift down, and then same signal go through this compensation capacitance. But the signal cannot propagate from the left to right, right? Because of this amplifier. So amplifier can be source follower or common gate amplifier like this. So capacitance there. In that case, this amplifier is put it in there, right? So this is source follower, or what? The C gate CG amp, right? So it can be the PMOS or NMOS device. PMOS transistor, NMOS transistor. In either case, it's fine. So we can use the current buffer. It's like this is common gate, right? The problem, so this kind of adding unidirectional buffer causes additional power consumption, especially the method 1 additional power or current. But for the method 2, using current, so this is current, let's say method 1 is source follower. So method 2 CG gate is, in CG gate there is an efficient way to add that function without adding power, or is possible. So that's why people use the second method. We will see in more detail. So this is second stage amplifier. If the first stage is cascode amp, and current buffer can be used through that the cascode device. We can reuse cascode device in the first stage amp, right? So the cascode this compensation capacitance can be added through the non-signal path or the signal path here, cascode. Those two response result in slightly different signal transfer function, but both have the Miller effect, the same Miller effect. So nowadays, the best performing approach is that we use both the kind of a hybrid approach, so that use both the non-signal path compensation and the signal path compensation. We put a half 0.5 cc and additional 0.5 cc. This is the output. So that is what? So half of the capacitance is connected on the signal path, and the other half is connected through the non-signal path, like this. So this is most popular. This is the most popular because it has the best second pole location, highest second pole location, and FG scenario, the zero location, right? This results in fast settling. Okay. So another way to remove the zero, positive zero, is to add the compensation resistor in series with the CC, like this. So this resistor can be implemented in the poly resistor or transistor. So what value of the RC is used? We can drive the equation similarly. Let's say if there is RC there, we can do the same analysis. So this current versus that current is the same, and the output equal to 0. So we can drive the equation for the zero location. So we can find the S. If you want to find the S, how we calculate? Drive the transfer function, force that to 0, and the S become what? 1 over C, right? So like this. So same method, we use the signal current through the CC path would be what? Vx over RC plus 1 over SCC, and the minus what? Vx GM2 equal to 0. So we can find that 1 over SRCCC plus 1, the SCC minus GM2 equal to 0. So we can multiply that one. So what? So we can find the zero location Vx the SRCCC plus 1 SCC minus GM2 SRCCC plus 1 0. So we have the GM2 RC here and GM2, something like that. If you find it as P as 0 here, then what? 1 over CC 1 over GM2 minus RC, right? That will result in that equation. So as you can see, if the compensation resistor is exactly the same as 1 over GM2, then the 0 will be infinity. 0 will be at the infinity. If the RC is slightly larger than 1 over GM2, then it will be on the negative 0, right? So negative 0 adds additional the phase shift, but it adds up the phase, so it helps the PM. So help PM, so help PM. The positive 0 is evil. Positive right half plane 0 is we must avoid that. So we can design that value in that way. So the controlling RC is difficult by the R. So we have by triode, and also the RC in poly register, and poly register is also process dependent. Vary. By PVT process and temper process. So exact value, controlling exact value is difficult, so people prefer not to use these days. Okay, so people not use not that much in this approach is not popular nowadays. So let's target how in our initial design what value of the RC must be chosen for initial design. So we will consider that if the RC is much greater than 1 over GM2, then it will be left at plane 0. So left at plane 0, negative 0. Then its 0 location is at the what? This frequency, right? RC, CC, right? We will place the 0 location at the finite location, depends on the RC. So, but if you target that 0 location at the 3 times FU, then it will have a proper, we can we can get the best gain margin, because if you remember that we'll have this kind of things, F2 location and the FG, and here FU here. So if for F2 location is approximately 3 times FU, then we get the PM 70 degree, right? We can do similar, so FG2 also 3 times FU, then the response will be flattened out. This second pole and 0 will be at the same location. So if you place that, we can get the straight line of the gain response. So, but if you get below that, then what? So you will have like a 0 and F2, something like that. This is something not wanted, so avoid. So this is the limit for the 0. So if the 0 location, so we want to have a very high frequency, or at the below, so at least we want to maintain the 0 at that the 0 at that 0 greater than F2, right? So for that case, what would be the GM? So if you consider that, so F2, if the F2 is what? If the F2, FG is 3 times F1, that means that 3 times FU, that means 3 times GM1 over CC, right? So this equation and that the above the equation, 0 location 2 pi CC. This is, let's say, 2 pi over that, and then 1 over GM2 minus RC. So CC 2 pi cancel out 3, so what we have is 3 times GM1 1 over GM2 minus RC equal to 1. So RC is what? 1 over GM2 minus 1 over 3 times GM1, right? So if you assume that the for CC is about half of the CL load capacitance, then the GM2 will be 8 times GM1. So in terms of GM1, so 8 times GM1 minus 1 over 3 GM1, that give us let's drive that in terms of the GM2, then what, 1 over GM2 minus 3 times 8 GM1 that the so let's drive that again in the next slide, getting the space getting smaller. Okay. Let's recalculate. So FG here is that 1 over 2 pi CC 1 over GM2 minus RC. So we place that the 3 times FU around that, this condition, then the if that would be GM1 over CC. So if RC is greater than 1 over GM2, then we can approximate that one minus that one goes to 1 over 2 pi CC RC, right? So that is this is just approximation there. CC 2 pi 3 times 2 pi there. So therefore the RC is cancel. So equal 1 over GM1, right? So we just place that ignore the negative things. So the magnitude wise, if you place that 0 around this the 3 times FU, then RC must be close to 1 over 3 GM1. So the choice of the RC, first we would like to start from the same RC equal to 1 over GM2, then the zero location, let's say zero location will be at the infinity, right? And then if that RC is greater than this 1 over GM2, then it will start showing the zero location, right? Then it will go down and down up until the FU, and here the 3 times FU, around 3 times FU we would like to stop there. So if you go increase until when 1 over 3 GM1, in that point the zero location will be aligned with the 3 times FU. So this is kind of a range of the RC that we would like to put in there. So using that fact, in terms of the GM2, we can represent the RC, range of the RC. For CC equal to 0.5 CL, and GM2 is 8 times GM1, right? If you remember the previous derivation, then the overall RC range is 1 over GM2 to 8 times 8 times over 3 GM2. So around the 1 over GM2 to around 3 times of the GM 1 over GM2 is kind of the range there. So you can design the RC slightly larger than the 1 over GM2. That will give us a good choice of the RC, right? So design RC. So design RC slightly greater than 1 over GM2. Okay. This is the example or exercise. For example, if our target is GBW, FU is 50 megahertz for load capacitance is 2 picofarad, then let's design the current level and compensation capacitance and CC. So we would like to choose compensation capacitance, just half of the load capacitance, for example, and then choose that. Then since we know that GBW, we can choose that the amount of a GM1 required the GM1, that would be so by the GM1 over CC is the FU. GM1 over 2 pi times CC is in FU. So this based on that, so this FU is at 50 megahertz. So plug that number there. So we would like to get require the GM1 is 315 micro Siemens. Then once we know that, we can design the current level. How much current level we would like to have? Approximately the GM efficiency. Assume the GM efficiency is I over GM over I, approximately 10. So assume that this is the efficiency that we assume. In that case, then the required current level is 1/10 of the this GM1. That would be 31.5 microamp current level. Right now, the non-dominant pole. The location of the non-dominant pole, we would like to place that at least 3 times FU, right? So 150 megahertz. Now the non-dominant pole, second pole location is what? By the GM2 over 2 pi CL, right? Approximately. So we put it in there. For rough margin, we put a 4 factor, so 4x, we design for 4x times FU in this example. So in that case, GM2 required the GM2 is 2520 microsiemens. So again, the GM efficiency about 10. We require the current level is 252 microamp, right? Once that is found, GM2 is found, each one of GM2 is 400 ohm. So we design that RC greater than between 400 to 1 kilo ohm, right? So 8 over 3 times what? The R 1 over G. This is 1 over GM2 2, right? The RC GM2, right? So about 1 kilo ohm range. So we choose that RC slightly greater than 400, that is 640 ohm. So we can we will consider that the process of variation, for the variation of a 60%, still our circuit works fine. We can verify that in the simulation. Consider verify in simulation, right? So this is just brief idea of the how we get this, the how we design the components for the required the amplifier spec. Okay.